The IP layer, and we will see three topics: ARP, automatic configuration, and a few words about TTL in particular. ARP, or MAC Address Resolution, is one of the less understood things of IP, but it's very easy to understand if you remember the principle of IP. IP is interconnecting subnetworks. And the problem is now, once through the use of the network mask or going through the routing table, the IP forwarding has decided that it has a packet to send directly to somebody. That somebody may be the final destination in the very first case, or it may be the intermediate hop, the next router on the path in the second case. In all cases, the problem is now, how do I send directly to the next hop, which is in the same local area network as me, in the same subnetwork? Well, the only, well, it's trivial. You create, if you're an Ethernet, you create an Ethernet frame, and you put destination MAC address, the destination of the next hop. The only non-trivial thing is, how do you find this destination address? So what is, for example, the MAC address of that destination? Then we need an address resolution procedure for that. How do we find the IP address? How does my client know how to go to the IP address? Yes?
We ask the DNS server.
We ask for DNS server if we're a client going to a server. If you're a server going to a client, usually it is, we learn it from the source address. So we have an application layer mechanism, or we're responding to something to know the IP address. How can we find the MAC address? Well, it's more tricky because you don't know the MAC address of a server, for example, of a web server. Most of the time, you don't need to. The idea here is very typical of the 80s. This is how many protocols were done in the 80s. When you want to find an address, there are always, or we want to resolve a name into an address, there are always essentially two ways to do it. Either you go to a directory service. This is what we do with DNS. DNS is a directory service where you have all the names and the IP addresses that correspond. So you have a database somewhere that gives you all the mapping. Or you broadcast to everyone, you shout and saying, who has this IP address? Give me your MAC address, for example. We can use that for DNS also. When we talk about DNS, we'll see this is done by protocols like Bonjour for finding a printer. If you want to find a printer that's in the same local area network, you don't put the address of the printer in the DNS, but you simply ask anybody who is this printer. So this idea of sending a broadcast inside a network is very typical of local area network technology. Local area networks are drawn like this, like a shared medium. We'll talk about that next week. But local area networks were thought as being shared medium. So the idea of shared medium implies that it's very easy to do broadcast. So it was very easy to do. It's been used and abused. So the solution for IPv4 as well as IPv6 is to broadcast. So this machine has a packet to send to that to 15.7, which is this guy. What this machine will do is send a broadcast packet to, which means it will be received by everyone. It's broadcast in the local area network. It's not sent to the entire internet. No, it's impossible to do this. But inside the local area network, broadcasts are possible, and they are even frequent. That's a major difference between local area networks and the internet. In the internet, we don't do broadcast. You cannot send a packet to all IP hosts in the world, but inside the local area network, you can send a packet to all the hosts in the local area network. So this is what will be done. So this packet is what? It's called an ARP packet. In the case of IPv4, it's a special protocol. It's not IP, it's a special protocol called ARP that is there only to contain the ARP request and ARP queries. In the case of IPv6, it's an IP packet. In fact, it's an ICMP packet. ICMP is the control and management protocol of the internet layer. So it's correct, in fact, to put it in ICMP. It's something you do because you need to have more information about how to use the network layer. So it's a management packet. But those are minor details that are visible when you do a Wireshark, but they are not so important. The important thing is the destination is broadcast, which means in the case of IPv4, it's sent to the broadcast MAC address. Broadcast is all bits equal to 1. So in this case, all Ethernet adapters will receive it. They will copy it. Then they will see it's an ARP packet, so they will analyze it. So LRCPC2 ED0X will, the Ethernet adapter and the operating system will be disturbed by this, will read the question, and they will see, oh, it's not me. In principle, they will do nothing, except if they are malicious. If they are not malicious, they will not do anything. And only STI SUN1 will respond. And it will respond, of course, to the source. So it will send to the MAC address of this machine. How does it know the MAC address of EDI21? It's in the source address field of the MAC packet. So it will send to that MAC address. And inside the MAC packet, there will be an ARP packet that will say, I am this IP address and I am that MAC address. And ED2 minus IN will believe this and will therefore think that the MAC address is the one that corresponds. And now now the IP packet will be sent here. So there will be 2 packet exchanges before being able to send 1 packet. This is how things are done today on practically all Ethernet and Wi-Fi networks. In IPv6, it's exactly the same thing, except as usual with IPv6, the details are a bit more complicated. The IDs are exactly the same, but the details are sophisticated. First sophistication is that it is an IP packet. The ARP packet is an IP packet. So to whom should you send an IP packet where you ask, who has this IP address? Please give me your MAC address. Well, you don't know to whom to send it. So you could send it to the broadcast address, which exists. Also, you could send to all local area, all systems in the local area network. In IPv6, people don't like the idea of broadcast, so instead, they've tried to do something that they believe is smart, at least is complicated. It consists in sending it to an address that is in some sense derived from the final destination address. So it's called the solicited node multicast address. So it's a multicast address. Multicast means it's not the address of one machine, but to a group of machines. And here, what is the group of machines? Well, it is all the machines that have the same 24 low-order bits as the final destination. So this guy is looking for this entire long IPv6 address. If you look at the end, the last 24 bits are given by the hexadecimal digits 6600001. 24 bits gives 6 hexadecimal digits. So those are the things in red here. You prepend this to a prefix that gives you a multicast address, and this has a name. It is the solicited node multicast address. And the hope is that you're sending to you don't know whom, but it's very unlikely that there are many machines that have exactly the same address, because most of the time it's the low order bits that differentiate different hosts in the same local area network. So the most likely case is there is only one machine that will respond to that address. They will be listening to this group, and it will be STI SUN1. Why do they do this instead of a plain broadcast? Has advantages. If IP multicast is implemented well, it means that those machines will not see the packets because they are not subscribing to this group. They don't subscribe to the group because their addresses does not have the same termination, so they will not subscribe to the group, so they will not receive this packet. That's the reason. Other than that, the things are exactly as for IPv4, except this tricky derivation of the solicited node multicast address, which is given here in all details here. Voila, my alarm is ringing, which means we do a break. We resume in 15 minutes. Multicast instead of broadcast. IPv6 does the same as IPv4, which is send some packet to, we don't know whom, but in principle to everyone over the local area network asking for the MAC address. The terminology is different. In the case of IPv6, it's called NDP, Neighbor Discovery Protocol, rather than ARP. And as I said also before, the difference is we use now a multicast IP address, which also means that the MAC address will be a multicast MAC address. We'll talk about multicast MAC addresses next week, so I'll skip this part. This multicast IP address is called a solicited node multicast address, and the only difficulty, which I hope for you is not a difficulty, is to be able to understand how we go from compressed to uncompressed form. How do we extract the last 24 bits of an IPv6 address? The good news is that with hexadecimal digits, it's much easier to extract bits than with decimal digits. Right. We see here, in particular, if the number of bits is a multiple of 4, which is an integer number of digits. This is supposed to be better than broadcast because we don't send the packet to everyone. Now, what remains to see is whether multicast in the LAN is not handled by broadcast. We'll talk about that next week. Many LANs do handle multicast by doing broadcast, in which case there is only a dogmatic difference between the two. The practical difference is 0. The rest is, as you can expect, once you get the answer, you know the MAC address, and you can therefore talk to this guy. In both cases, IPv6 as well as IPv4, of course, we don't do that for every packet that we need to send. That would be very inefficient. We do it only when there is a need for that, when we don't know the MAC address of this. So it's probably, so this is a router, this is a host on this LAN. It happens probably for the first time when somebody sends a packet to this machine, which happens perhaps once per, if the machine is, or once per session where the machine is activated. Right. Whenever ED2 minus IN has learned the MAC address of this destination, it will keep it in what is called the ARP cache or the NDP cache. And we'll try to, what is a cache? A cache is a local database which is meant to be temporary. It's learned on the fly. And typically you want to keep it as long as possible by refreshing it. A cache is a table where there is the correspondence, destination IP address, destination MAC address, and an expiration date. It will expire in a few minutes. What happens when it expires? Well, if there is no traffic at all, then it will expire. But of course, what you will try is, before it expires, you will try to refresh it on the fly, for example. This might receive a lot of traffic from STI-SUN1 because STI-SUN1 is probably talking to someone. Most applications are two-way. If A talks to B, there is practically always some traffic from B to A. Even if there is no application layer traffic, but if you use TCP, for example, there are acknowledgements. If you don't use TCP, you use UDP, and you must have a way to detect that there are losses, which probably means there are application layer acknowledgements. So practically all applications, with very, very few exceptions, are both ways. So there will be traffic coming back. So this one will be learned, will be able to check whether the IP source address of this guy corresponds to the MAC address it has in its cache, because the IP packet is contained in a MAC packet, so the two addresses are visible. And whenever it has a confirmation that this neighbor corresponds to the binding that is in the cache, it will refresh the thing. So if there is continuous traffic, there will be no ARP packet or no NDP packet. Once in a while, when this guy shuts down, then the cache will expire, and when it boots again, there will be one ARP or NDP packet sent. For IPv4, this is how they look like with the Wireshark. So this is an ARP packet, so we see it's an Ethernet packet with that source, that destination, which we see FFF. Inside the ARP packet, we see, inside the Ethernet packet, we see type ARP. So this means the Ethernet layer has a protocol type special for ARP. So it's not an IP packet, and it's a special protocol of its type that says essentially what is the target IP address. That's the only thing that's useful. As usual, protocols are usually verbose. They give a lot of information that may be useful for debugging. Originally, ARP was meant to be a universal protocol for address resolution that would work for all network layer protocols. It was done in the 80s. In the 80s, there were many network layer protocols, not just IP. There were AppleTalk, Novell Netware, etc. Each manufacturer had their own network layer protocol. And the idea of the people who did ARP was we do ARP for all the protocols. As far as I know, it was used only for IPv4, but this is why we found all those things here. Protocol type, here we say, for example, we are asking the question about which protocol, this field, which means IPv4. IPv6 does it a bit differently. From the Ethernet point of view, this is an IP packet. So it's an IPv6 packet, of course, that contains inside the IP header a next header. Next header means what is the protocol that is contained inside the IP packet, and in this case, this is ICMP. This software pretty prints in the form ICMP v6 because it means it's ICMP when used by IP. But it's not the 6th version of ICMP, it is the version of ICMP that works with IPv6. Remember, ICMP is the protocol that is used to control and manage the IP layer. So it contains the error messages and here a typical management message here. If we change the label, if we would put ARP here, it looks very similar to what we had done with ARP. Of course, the addresses are a bit different. They are multicast. And there is ICMP inside IP. Does it mean that ICMP is a transport layer protocol? Some people will say that. I'll leave it to them to say so. It is contained inside an IP packet. Therefore, you can call it layer 4 if you want. But most people today would agree it's not a good idea to call it layer 4. It's really the management of the network layer. Let me skip this one. No, I wanted to go to this one. Let me skip this one, which is too easy. Of course, as you have noticed, all of that is completely unsecure. If you have a packet sniffer that responds to all the ARPs, you're able to capture, and if you do it before the legitimate packet, you're able to capture the traffic that goes to an intended host. And you can do that on Wi-Fi. It's an attack against Wi-Fi network. Or you can do that on Ethernet network. How do you prevent that from happening? There are different ways to do it. On Ethernet network, this is what is typically done. The ARP traffic will be intercepted by the switches, by the layer 2 equipment that will look at all the ARP traffic and will check it or even possibly directly respond to it. Which means essentially we are taking away the broadcast idea and replacing it by a database idea. If you're in an enterprise network which is managed where everybody knows where every port should be, then you can check whether a given MAC address is supposed to be in this equipment, and then you respond for to the ARP instead of the destination. This is done, I would say, in banks, in highly secure wired network. It's not done at EPFL, for example. So on Ethernet, you are able to, if you can sniff traffic, you're able to spoof Ethernet. So Ethernet is assumed to be more secure because you need physical access, but the security is limited to that. On Wi-Fi, this is susceptible to attacks if you use a non-encrypted, non-secured Wi-Fi access point. We'll talk more about the MAC layer next week. If you use, for example, on the EPFL network, which requires you to authenticate, then of course the ARP, the management of the Wi-Fi network knows exactly your IP address and also your MAC address. So the ARP broadcast spoofing will not work, and ARP addresses can be replaced by what is called dynamic ARP inspection or even dynamic response to ARPs. Voilà, that's for ARP. A quick question to verify your understanding. P.H1, which is here on the left, sends a packet to Q.H1, which is here. What will happen? And assume the system has freshly booted, so all the ARP caches are empty. What is going to happen? So NDPNS is the IPv6 way of calling ARP, Network Discovery Protocol, neighbor solicitation, which means an ARP request. I close the poll. And the majority is right. So of course the packet will be sent to whom? Well, the packet is to IP destination address this guy, but the source and destination are not in the same local area network, so the source will look at its routing table in order to find to whom should I send the packet. It will send it to its router, which corresponds to the IP address P.1. So the routing table will say next hop equal P.1. So it will send to the MAC address that corresponds to the IP address P.1. So answer 2 is the correct answer. Well, that's for ARP. Now, the ugly side of IP is, as we said before, this subnet part, and the IP address itself needs to be allocated to your machine. When you come into this room, if you don't start your PC for the first time, when you come to EPFL for the first time in the morning and you boot your PC, your EPFL will obtain an IP address, which depends on which Wi-Fi base station you are connected to. You don't have to configure it manually, like you may need to do, for example, if you want to control, have more control, like we do in Lab 1, for example. What do you need to configure? For every interface, you need to give the IP address and the mask of the interface. This is needed for the IP algorithm to work. Then you need also the IP address of the default router. That's the minimum thing you need. If you have several routers connected to you, you need a full routing table. But for hosts, most of the time, all you need is one default router, which is called typically default gateway. And also, for other practical reasons, you need the IP address of a DNS server, because you will need the DNS to resolve names to IP addresses, But the thing you cannot resolve is what's the IP address of the DNS server that you want to use, because you cannot go to the DNS for that. So that's the 4 things you typically need. It can be done manually, and you've learned in the lab how to do that. But of course, most people don't want to do it manually, so you do it automatically. And the way to do that is called DHCP, Dynamic Host Configuration Protocol. Question?
Yes. Can't we find the router closest to me using an ARP?
Yes, we could use a broadcast, and we will see this is called a stateless auto configuration, which is typically done with IPv6, but not with IPv4. So it can be done by means of this, which involves a server and a configuration that's done by someone. For IPv6 it's the same. It can be also done completely automatically without anybody configuring anything. It's called stateless. We'll see why it's stateless. Auto configuration. And then there's a mixture of the two, DHCP stateless, which combines the two here. The only thing that's difficult is to know what it is doing. Then if we imagine how you can do it once you know what you want to do, it's probably straightforward. So what do we want to do? We want that when a machine boots, it should be able to get the information it requires without having the information that is required to participate in a network. So it's really a bootstrap problem. How can you solve? How do you typically solve such issues? Well, we've seen ARP, we've seen similar things. You send a broadcast out there asking, is somebody a configuration server around me? Like you send a broadcast if you want to find a printer, for example. And if somebody is a configuration server, then he will respond to you and give you the information. This is how it's done. So what you need is to have in your local area network is to have a DHCP server. Imagine for a second, this would be a DHCP server. If there is in every local area network a DHCP server, then you can send a special packet, which is broadcast, to the here IP destination. You see for IPv4 destination address is the broadcast address. So you send it to anybody, and the protocol that's contained in this packet is the DHCP protocol. So in principle, only DHCP servers will respond to that. Again, it's not secure. There might be somebody can put a rogue DHCP server in your network and then will give you false information. Although here the attack is less interesting. So this was assuming that I put a DHCP server in every local area network. Imagine at EPFL there are hundreds of local area networks. You don't want to have one server in every local area network, so you may want to be a bit smarter. How can you be smarter? Well, you can have that inside every local area network, you put a function that I call a DHCP relay. That is something that simply intercepts all those requests and sends them to the DHCP server. So instead of putting one server in every local area network, you put one relay. Now you will tell me, but you still need one relay in every local area network. That's not a big gain. Well, the gain is still the relay doesn't have to have the configuration information. Configuration information is for each of the machines here, which MAC address which IP address I will give to this machine. It doesn't need to have this information. So that's a gain, but the gain is minimal. The trick is, of course, that this DHCP relay function is implemented as inside the router. That is the default router for this local area network. If you have a problem with many local area networks, that means you have a network with routers. So an obvious place to put this function is inside the router. So when you buy a box that's called a router today, it will do a number of things. One of them is the true router function, intermediate system of the IP layer. But it will do also something else, which is called a DHCP relay, which is an application for auto configuration. and it's a relay function that's done here. So apart from this little trick, the thing is fairly obvious. So once your machine boots, it will send this broadcast packet to all DHCP servers or relays. The DHCP relay, which is some code in your default router, will receive it. And of course, your router is working. It has a valid IP address, so it's able to communicate and forward the relay over, for example, several hops to the DHCP server. The DHCP server will receive this request. So the request contains essentially some information about the client, which may be called a token, but the main information perhaps is the MAC address of the client, and will send, and it knows also from which relay it comes. So the relay knows on which port this has been sent, so it knows on which subnet this client is. So all this information can be passed to the DHCP server, who will allocate an address. Of course, the prefix is the one that corresponds to the port, and the host part will be whatever the DHCP server has been allowed to give to DHCP client. Typically, you reserve a block of addresses for this dynamic use. If you have a few servers on your LAN, you would not like that the servers get their address from DHCP. You want the address to be permanent. So in that case, you will exclude the address from the port. I have an error message from RW Poll. Okay, thank you. It works with IPv6, it worked with IPv4. It was invented with IPv6, and that was when IPv6 was created in the 90s. That was one of the main advantages over IPv4, that address allocation could be automatic. But of course, there's nothing in the nature of things that require the specificity of IPv6. What is the specificity of IPv6 compared to IPv4? More addresses. It has a huge address space, whereas IPv4 is very constrained in address space. But for that, you don't care about the address space. I mean, the request is sent to the broadcast address, and this relay router has IPv4 address. So, of course, it was retrofitted to IPv4 very quickly. Let me skip this one. So this is how addresses are allocated typically over local area network, ATPFL, for example, when you use the Ethernet network or the Wi-Fi network. Sometimes when you use other networks, for example, when you connect your ADSL modem to the ADSL infrastructure of a telecom operator, they do use variants of DHCP. One variant of it is called PPP. It's called the point-to-point protocol. Other than the name, for us, it is exactly like DHCP. It's a protocol that will make that when your modem starts, it talks to the router at the end, or the PPP server at the end, which is located in the router, and will obtain automatically an IPv4 address. So it has a different name, but apart from that, for us, it's like DHCP. In IPv6, and to some extent also in IPv4, as we might discuss, there was another idea which was inherited from Apple in the 80s, end of the 80s. If you would make a network with a few Macintoshes and printers, you made it without any configuration. In fact, it was completely plug and play. Now, Apple has lost this. You need a bit of configuration. You need to put IPv4 addresses. And the idea was based on the need to allocate addresses automatically without having to go to server. The typical case was mentioned as the dentist's office. You're in an office at home or in an office. You have a few computers, a few network file servers, printers that you want to connect. You don't care about the addresses. You're doing this in your local environment. You would like that all address allocation is completely automatic. This is also available in IPv6, and here is how it works. It's not so exciting. It's more a nuisance than anything, but it's important to go through it because we will see visibly when we do Wiresharks, we will see addresses that come from those things here. In particular, with IPv6, what is special is the concept of linked local address, or it exists also in IPv4, but what is special in IPv6 is that it is used always. In IPv4, it's more an exception than the rule. A linked local address, remember, link means local area network. It means subnetwork. So linked local address means an address that's valid only inside my local area network. Someone else might have the same address in another local area network, and that should not create a conflict. It's not the same as private addresses. Private addresses can be routed. You can build a network with 200 routers, all made of private addresses. Here it's private in some sense, but it's not called the private addresses. It's addresses that are meant to be used only in the local area network. If we go to the end of this logic, we could remove entirely the MAC addresses and use only the linked local area, the linked local addresses, and perhaps it will come one day when there is only IPv6. Apart again from the addresses, the thing is almost trivial. If you want to allocate to yourself an address, so my PC boots, and it wants to find an address. The first thing it wants to do is find its linked local address. So linked local address means an address that does not have a subnetwork prefix. So I don't need to discover in which subnetwork I have. What's the only thing I need to check? Well, it is that someone else doesn't have the same address as me. So the only thing you need to do is an address duplication test. So you do a duplication test. So when this machine boots, it will automatically create from something its linked local address. In fact, it will derive it from its MAC address. We've seen that in lab 0, I believe. We've seen how or in lab 1, we started seeing that. So you take the MAC address, you add a few bits to it, and that gives you a 64-bit token that you can add to a well-known prefix, which is FE80, which means linked local address. And that, in principle, should be your address. Your MAC address should be unique. If somebody hasn't hacked MAC addresses, that should be your only address. Now, you can never guarantee that MAC addresses are unique, so you will do a duplicate test. How do you do a duplicate test? Well, if you would be in IPv4, you send a broadcast in the local area network saying, or you send a packet to this address. Here, it's done by doing a packet sent to the multicast address derived from that target address, which is the same trick we've seen before for the IPv6 version of ARP. So it will send it to this multicast address, which nobody listens to other than guys that have the same address here. Nobody will respond, presumably. And after doing a number of attempts and receiving no response, you will keep this address. So that's the first step. If somebody responds, you have a problem, this address doesn't work, and probably your machine will say unable to start IPv6 or something like this. You have a problem that you need to fix by talking to your system manager or destroying another machine or doing something. Here what I mentioned is derived from the MAC address. Now there is a flurry of possible ways of allocating this token. TPFL, it's typically done by a predefined rule. There are Microsoft operating systems doing by doing a randomly assigned address. Why would people prefer to do something complicated rather than simple? Can you guess why? There is an issue with having the MAC address, yes? Security or privacy, where you start revealing your MAC address to other machines. Although you could say here it's in the local area network, so you will reveal it probably in a number of other ways. This is how it is done. The randomly assigned address is the randomly host part of the address We will see later that, of course, the host part of the address, you can use it for a globally assigned address, not just for your locally assigned address. So once you do this, if you use your MAC address and you go to a web server that's at the other end of the world, you start revealing your MAC address to the web server that's at the other side of the world. In the 90s, that was perceived as a problem. If you do that today, probably you reveal everything to the server. If you're doing over an iPhone, you will send the number of the iPhone and everything. You will send it also to Apple that you're talking to this server. So, but if privacy is a concern, which is a concern for some of the designers of this, then you don't want to use your MAC address as your host part. So you can use a randomly assigned address. Now, the problem with the randomly assigned addresses is if you keep it constant, then at the end of the day, it's like a MAC address. It identifies you if it's always the same. It's random, but it's always the same. So by knowing what you do on the server, we know, oh, this is this guy coming up again, the guy who bought all of this wine last week and is likely to buy like this one, etc. So you don't want to do this. You want to change the IP address. So if you use random addresses, you will change them once in a while, which means the addresses will have limited lifetime. If the addresses have limited lifetime, that means they will die. And if they die, you have to renew them. Of course, if you renew them brutally, abruptly, you will break all established communications. We will see that in TCP, if you change your IP address, all the TCP sessions all the TCP connections are broken. So if you're transferring data from YouTube and you change your IP address because Microsoft Windows 10 decides that it has been used long enough, then you break the connection. Now, no big deal, but you prefer perhaps not to do it, not to break connections because of this. So in IPv6, there is the concept that you do it smoothly. So you acquire an address, and while this address is acquired, it remains your principal address, the preferred address, until it becomes stale, deprecated. It's no longer valid. But when it's no longer valid, it is still valid. That's why it's called deprecated and not invalid, which means you will not establish new connections with it, but the old connections that exist will continue being used. So in the unlikely case that you maintain a connection during 2 years, that will not help hiding you, but if you're maintaining a connection during 2 years, you cannot hide anyhow. But in most cases, for most clients, the thing will break sooner or later, and more soon than late. So what will happen when you're in this phase, this address continues to be used by your machine, but any new connections will use a new address that was allocated to you. To make a long story short, what it means is that with IPv6, the same interface routinely can have several IP addresses that are valid, allocated to the same address. This is where we see when you give things to people, they use and abuse it. So with IPv6, what do we give to people is lots of addresses. Now you have lots of addresses, so of course you need many per interface, unlike with IPv4. I skip a few quiz. I will put the solutions online. You can look at them later. So if you do this automatic allocation of addresses, and if you're alone in the world, you're on an island in the Pacific Ocean, you have your printer, your computer, a solar panel for powering, and you want to connect the two together, this will be sufficient. You don't need a network prefix. You can live only with link local addresses. So we see here that there is perhaps a hidden agenda in IPv6, which is to get rid of the MAC layer. I mean, if you replace the switches by IPv6 routers that work only with link local addresses, then you do exactly the same as the MAC layer. So some people say that in a distant future, when there is only IPv6, so all IPv4 systems have been disconnected, we will not need the MAC layer because IPv6 has all the mechanisms to operate only in a subnetwork where there is no router using these link local addresses. We're not there. So today, most of the time, you're connected to a router, and you need to know also what is your prefix, what is the subnet part. Somebody suggested, why go to DHCP? Why don't you ask around who is a router? Most of the time when you're at home, you have one router. So you can ask around who is a router. Your ADSL modem will say me, and here is the prefix that corresponds to the port on which I have received this request. This is exactly what is done here. It's called a router solicitation. Once you have acquired an IPv6 link local address, you can use IPv6 in the local area network. So you can use a broadcast, or of course with IPv6 you can say we don't broadcast, we send a multicast. This multicast address, FF is a prefix for multicast addresses, FF022 means all the routers that are on link. On link means in the same local area network as me. In principle there's one. But there can be cases where you have several routers. If you have, for example, a local area network that is used for mission critical servers, you may have several routers that interconnect this to the rest of the world so that if one of them dies, the system continues to operate. So whoever is a router will receive this and will respond with a prefix that corresponds to this local area network. That's the green part. This host has received the green part. Now it has its complete address, and it's different than DHCP. There was no database that's doing it, but using only local information, you have received all of this. I have lost the connection to RW pole or turning point, so we will not do the quiz. A small variant of this is called Stateless DHCP. Again, looks very complicated, except if you try to understand why it's been invented. Well, it's been invented to fix a problem of stateless auto-configuration. The stateless auto-configuration doesn't give you everything. For example, it doesn't give you the IP address of the DNS server. Now you could say the routers perhaps know the IP address of the DNS server, except typically you sometimes may want to separate the router infrastructure from the DNS. The routers are animals of their own. The DNS is run in a different way, so you don't want to put that information in the routers. So you may want to put it where? Where? In a DHCP server. So if you use this method, when an IPv6 machine starts, it will obtain its IPv6 address for all of its interfaces, and the things that are missing, it will send them. It will ask them to a DHCP server, but it will not ask the DHCP server for IP addresses, but just for the IP address of the DNS server. It's called stateless because here the DHCP server simply is like a DNS server. It's responding only one question, which is always the same, which is what is the IP address of the DNS server? And in principle, it doesn't care who is asking that question, as long as it's somebody that's coming from the enterprise network. Voila, I will just mention that similar things exist with IPv4, but are much, much less widespread. They are called IPv4 link local addresses. If you are on your island in the Pacific and you're running IPv4 rather than IPv6, it will work the same way, with a different terminology. What your machines will do if they deploy this, which is the case for, as far as I know, Windows and Macintosh, it will use one address of that block, which is the block of link local IPv4 address. Of course, it will not have all the beauty of IPv6. It will not use all that sophisticated terminology. It will send broadcasts, and it will be able to operate with one IP address that can be used only locally. As far as we know, we've tested, the Linux versions we have don't support this. But I'll skip this and I will move to the last interesting parts of this chapter, which is the TTL. So we move to the last section of this chapter, which can be introduced by looking at what's inside Wireshark when you look at an IP packet. If it's an IPv6 packet, what do you see? We've already discussed that. You see the source addresses, of course. You see the next header, which indicates whether what is contained here is a true transport layer stuff, TCP UDP, or ICMP. We will see other examples when you have IP in IP, for example. It contains a few things that are useless, like the version, it's always one, the traffic class, which is never used, the flow label, which is never used, and the payload length, which gives the size of what is contained here. So this one is useful. And something very useful that I will discuss now, which is the hop limit. The hop limit is called in IPv4 the TTL. So IPv4 is very similar. It has also useless fields. The next header is called the protocol. And time to live is the name that it has for the hop limit. When IP was invented, it was a time measured in seconds. Of course, now you don't monitor the time that a packet lives. What is it? It is a field that is coded on 8 bits, so it is between 0 and 255. And it's decremented by 1 whenever a packet is forwarded. When it goes through a router, you decrement this field. Why would we like to do this? Yes?
Count the number of hops.
To?
Count the number of hops.
To count the number of hops, yes. Yes?
It's to avoid having packets wandering forever among them.
To avoid having packets wandering forever. That's the primary goal, is to avoid loops. In the internet, in principle, there's no loop. But if there is one, which can happen at least if your routing tables are ill-configured, I mean, you can manually in the lab configure the routing tables as you want. So you can have router A send to B, B send to C, and C sends to A. Should not happen, but because this is based on configuration, you cannot entirely exclude that once in a while it does happen. It might happen, as we will see, the routing protocol, some routing protocols have long convergent times, so that it might happen while the routing protocol has not yet fully stabilized, or by true configuration errors. Somebody in some network, a fresh guy who just graduated from EPFL has the goal of running the Swisscom network and does a configuration error, and bing, there's a loop. Right? What happens if there's a loop? Well, all the packets will follow the loop. Now, if the propagation time is not very large compared to the transmission time, it might be that a single packet goes very quickly from one part of the loop to the next. So it might be that with a very small number of packets, the loop is entirely busy. Perhaps in the worst case, you can imagine you have a loop of 3, a triangle, and 3 packets are busy going from one to the next. So with an extremely small number of packets, you can fully utilize the capacity of a link. So it's the ideal denial of service attack if you can create loops. We cannot avoid them entirely, but what we can do is mitigate the effect. If your packet has circulated very quickly, the TTL will be decremented, and after doing a number of rounds, the packet will be discarded. So that will not solve the problem of the loop. The packet will not reach the destination, but it will prevent the denial of service attack against the thing. So the algorithm is, if you're an IP system, you receive a packet with a TTL or a hop limit. If the hop limit is equal to 1 in the packet that you received, then hopefully this packet is for you. So you are the final destination of this packet. Okay, you accept it. If it's not for you, you have to forward it. But by forwarding it, you would decrement and create a hop limit of 0, which is invalid. So you kill the packet. If the hop limit is larger than 1, then you decrement. By default, I believe, as far as I know, the standard says it should be 64 at the source, but not all systems do it very strictly. We have seen a use of TTL already. This is how traceroute operates. How does traceroute discover the path that is followed by from A to B? Well, what it does is it sends a series of packets. So first, when I do a traceroute to a given destination, what the traceroute program will do is send a packet with TTL equal 1. What will happen to this packet? It will go towards the destination. In fact, it will go to my default router. the default router will kill it. Now, in principle, if you kill a packet due to an error, you send an error message, an ICMP message, back to the source. In principle, some routers do it, some routers don't do it. Routers that are in the backbone of the internet very often don't do it. Enterprise routers very often do it, but not all. So if the router does it, you will send an error message. Hello? That's almost the end. It will send an error message back to the source. Now the source, the traceroute program, will receive this error message, and it will know from whom this error message comes. It comes from the first hop on the route. Then traceroute will send a packet with TTL equal 2, so the router that is the second hop on the route will send me the error message, and this is how we create this trace here. Of course, if there are multiple paths in the internet, and usually there are multiple paths in the internet, there is no guarantee that this is consistent. Whoever sends this is whoever happens to be hop number 6 on the path, but there may be several hop number 6 in the path. And the hop number 7 is perhaps not the one that follows number 6, it depends. Voilà, that's all for today. See you tomorrow.